So we've been learning about buffers, and today we're going to learn more about buffers. The effectiveness of a buffer depends on a couple of things, and one of those things is the relative amounts of acid and base. So the buffer will be most effective when the concentration of acid and conjugate base are equal. So equal amounts of acid in the conjugate base. And we're going to look at two 1 liter solutions of a buffer, unnamed buffer. pKa is 5. And we're going to calculate the percent change in the pH when we add 0.01 moles of sodium hydroxide to each. Let's see what happens. So in this one, we have equal moles of acid and conjugate base. In this one, we have 0.18 moles of acid and only 0.02 moles of conjugate base. This has an initial pH of 5. So we can do this calculation. We look at our initial moles. So we are adding 0.010 moles of sodium hydroxide. So that goes first in our chemical equation here. That's going to react with the acid part of the buffer. We've got 0.1 moles of that. It's going to produce water and the conjugate base. And we also have 0.1 moles of that to start with. So then we look at the change. And it's a limiting reactant problem. This is the stoichiometry part. So this is smaller than that one. This one's going to get all used up. So we subtract 0.01 from this and 0.01 from that. And we add 0.01 over there. Everybody clear on why we do that? We're going to assume that this reacts completely. And so we're going to assume that all of this gets used up. If all of that gets used up, then the same number of moles of that will get used up. And so then we figure out how many moles are left after we've neutralized the added sodium hydroxide. Now, we can calculate the pH using the Henderson-Hasselbalch equation. So pH equals pKa plus log of base concentration over acid concentration. So we want to know what the pH is. On the previous slide, they told us that the pKa is 5.00. Then we need the concentration of the base. So we have 0.11 moles. Remember, they told us this was a 1 liter solution. So then it's 0.110 moles per liter. And we have 0.090 moles of the acid. So we do the math. 5 plus log of 0.11 divided by 0.09. You get subtracting and dividing, and so it can be all over the place. It doesn't really matter. So what I do is I just always use 2, and that's what generally what the my open math reports are going to ask you to do is 1 or 2, because we just want to have an idea of what the percent error is. So any questions about how I did that calculation? So then we're going to do the same thing with the other buffer. This also has a pKa of 5. Here's that same table. We don't really need to talk about it unless anybody wants to. I didn't think I'd get any takers on that. So the base is 0.03 moles in 1 liter, 0.03 molar, and the acid is 0.170. .2467. This had an initial pH that was different. Why is that? Were the initial amounts of acid and base the same as they were over here? No, they're different. This one had more acid than base, and so the pH of the buffer is going to be lower than the pKa. This one had a pH that was equal to the pKa because when it started, the concentration of acid and base were equal to each other, and so base over acid equals 1, log of 1 is 0, pH equals pKa. But over here, it doesn't. So, percent change, we're going to do the final minus the original. Four point 4.9%. So, two different buffers. This one had equal amounts of acid and base. This one had, in total, the same amount, a total of 0.2 moles of acid and base combined. 0.1 plus 0.1 is 0.2, 0.18 plus 0.02 is also 0.2. And we were adding the same amount of hydroxide to each of them. But we see that the pH change for this one was significantly less than the pH change over there. That make sense? So the buffer will be most effective when the concentrations are equal. Yes? I got the pKa from this. I couldn't find it yesterday, so I'm like, wait a minute, I need the pKa, and I looked back there, I couldn't see it, and I'm like, well, if these are equal and this is the pH, that's the pKa, so that's where I got it from. Yeah, good question. Anybody else? Oops. No, I'm going the wrong way now. Okay, so it's most effective when the concentrations are equal, but of course that's not always going to work out. So when is it reasonably effective? So it'll be reasonably effective when the concentration of acid and base differ by no more than a factor of 10. Okay, so, or you could say that the base concentration divided by the acid concentration is greater than 0.1, which would mean that the acid is 10 times larger, and it's less than 10, where the base would be 10 times larger. So with this guy, does it meet that criteria? Yeah, it does. Because if I take this and multiply it by 10, I get more than that. So they differ by less than a factor of 10. So that one had a higher percent error, or difference, percent change, but it was still reasonably effective as a buffer. Any questions about that? Another thing that affects the effectiveness of a buffer is the absolute concentrations. So the buffer is most effective when the concentrations are high. And we're going to look at the same buffer. Here they're going to have equal concentrations, but one of them is going to have concentrations 10 times higher than the other solution, and we're going to look at the percent pH change. So here, 0.5 moles of each, 0.05 moles of each. Because the concentrations are equal, the initial pHs are the same, equal to the pKa. So here's our little MICMA table. I'm waiting for someone to come up with a better name for that. MICMA's good? I mean, it could be worse. It has been worse, so. Half a mole of this and half a mole of that. We're adding 0.01 moles of this. This gets all used up, so we subtract all of that away to get 0. We subtract that from here, we add that to here. Same thing over here. We're just starting with different amounts of moles. Everybody okay? I know it's just a lot of numbers up there. But it's just like the stuff we looked at in the previous example. So let's calculate the pH of the solution after adding the hydroxide. So pH equals pKa plus the log of the base concentration. Here's our base. It's 1 liter, so 0.51 moles would be 0.51 molar. And the acid is 0.49. Get 5.0174. Percent change. Take our new pH and subtract the original pH and divide by that. 0.35%. So this change in pH was less than the good one on the previous example. These concentrations are 5 times larger. That one was 0.1, and this one's 0.5. So the amount of change in the pH is lesser when you have higher concentrations. And then we'll do the same calculation over here. And our base concentration is 0.060 moles per liter, and the acid is 0.040 moles per liter. 5.1761% change. .5%. So cutting the concentration by a factor of 10 made the percent change in the pH 10% bigger. A factor of 10 bigger, sorry. Any questions? So we can calculate the pH range in which a buffer can be effective. So this is going to be based on the relative concentrations of acid and base. So the lowest pH will be where the concentration of the base is 1/10 of the acid. So we don't know what that concentration is, but we can still mess up the slide. We want the base concentration over the acid. Well, the base concentration equals 0.1 times the acid concentration. And the acid concentration is equal to the acid concentration. So the acid concentration cancels out. And we get pKa minus 1. The log of 0.1 is -1. And do the same thing down here. Here, the base concentration is 10 times as big as the acid. So this ratio is going to be 10. And we're going to get pKa plus 1. So this becomes a guideline if we're trying to choose what sort of a buffer to use. We're going to choose one that has a pKa close to what we want, and we know it'll be effective within plus or minus 1 pH unit. So the effective range for a buffering system is 1 pH unit on either side of the pKa. So, you know, you may need a buffer that's pH 7.4, right? Like your blood. Well, you're going to choose the weak acid and conjugate base based on something that has a pH that's close to 7.4. There's a good possibility that you can't find one that is exactly right. But that's okay, because you can tweak the pH of the solution by adjusting the ratio. So you can bring it down a little, bring it up a little, and still have it be an effective buffer. Any questions? So which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? These are the options that we have. So which one would be a good choice? Which one's closest to 7.35? I know this is hard. HClO? Yeah, it's the only one that's even close. It's this guy right here, right? Those are all like down at 3. Those aren't going to be good choices if we want the pH to be 7.34. So this is the buffer we should use. This is the acid. So what we need to do to make the buffer is we need to add acid and the conjugate base. So let's stop and think about this. Here's our acid. How do we make sure we know what the conjugate base is? Well, write the equation for this ionizing. Here's our conjugate base. Acid, conjugate base. So it's saying we're going to combine it with its sodium salt. So a salt is an ionic compound. The sodium salt of an acid is where you take the hydrogens and you replace them with sodium. So this is hypochlorite, and so we're going to use NaClO because you can't just add ClO minus. It's got to come with something to be neutral. Okay? So we're going to be using, that's not at all what I meant to do. Started drawing straight lines. That's very nice, but so that's the salt. Everybody okay with that? That's something we should know how to do from Chem 1A, but it's kind of shaky. Okay, so that's the first part of the question. If you have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? And we're not going to use any tables here. We're just going to use the Henderson-Hasselbalch equation. So the pH of a buffer is equal to its pKa plus the log of the base concentration over the acid concentration. Do we know what the pH should be? Yeah, 7.35. Previously, we've been calculating the pH. Now they're saying this is the pH, calculate something else. The pKa is this guy, because this is the one that was closest. 7.54 plus the log of They're asking about the mass of the sodium salt, which is the base. So we don't know this concentration. Do we know the acid concentration? Yeah, it's 0.1 molar. So this is going to be the base concentration divided by 0.100. You following that? Then we have to solve this. If algebra is not your friend, use the solver. So the way I would solve this is I'd take the 7.35 and I'd subtract the 7.54. It'll give me negative 0.19. Is equal to the log of the base divided by 0.100. To get rid of the log, I'm going to take 10 to the x of both sides. So then I'm going to multiply both sides by 0.1, and I'm going to get, I should have a base concentration that is 0.06457 moles per liter. Now the rest of this is something you also learned in Chem 1A, but may have forgotten. How would we make a solution that is this concentration? We're going to add the sodium salt. That's going to be a solid. That's why they're asking us what mass. We're going to add that to the solution that we already have. So this is the volume of the solution, and this is the concentration that we want, right? So we have 500 milliliters, and we want 0.06457 moles per liter. This is really dimensional analysis. Molarity is generally a conversion factor and not the thing you start with. We're going to start with the 500 mils. And I think we're advanced enough now that we can just convert that to liters in our heads. I'm going to change color here so it's not as confusing. So that's going to be 0.50 liters. Sometimes people go the wrong way, and they'll say that 500 milliliters is 500,000 liters. Does that make sense? Not when you think about it, no. So, I like to remind students, how big is a milliliter, right? It's the bottom of the 10 mil grad cylinder, right? It's this big. How big is 2 liters? 2-liter bottle of soda, right? That's much bigger. So don't tell me that 2 milliliters is 2,000 liters, right? That's backwards. So one way you can avoid that is look at which of these has the smaller unit. Milliliters is the smaller unit, liters is the bigger unit. The small unit should have the big number, the big unit should have the small number, otherwise you went backwards. So what I'm trying to find is the mass of that sodium salt. The molarity is going to allow me to find the moles of it, right? I want 0.06457 moles per liter. And then I can convert that to grams using the molar mass. It's NaCl4, not ClO. There's no 4. Never mind. Let's start that again. It's NaClO. There we go. almost got it wrong again. NaClO, not just ClO. Common mistake would be to forget the sodium in there, right? So when we do the molar mass, we need the sodium plus the chlorine plus the oxygen. And then just go from left to right. I'm kind of going over this because some of you were not in my Chem 1A class. So after you get it all strung up like this and you've got your liters canceling and your moles canceling, just start at the left, multiply by the top. If there's a number on the bottom, divide by that. And just go across, and that way you don't have to write down a numerator and write down a denominator and divide them later. So 0.5 times 0.06457 times 74.44. There is a little bit of an assumption that we're making here that adding 2.4 grams to 500 milliliters is not going to significantly change the volume. But it's close enough. Any questions? So the buffer capacity is how much of an acid or a base can you add to the buffer without causing a large increase in pH. The capacity will get larger if you have larger concentrations of the buffer components, because there's more acid and more base to absorb whatever there is. The buffer capacity also increases as the concentrations of the buffer components, the acid and the base, are closer to each other. So if one is, 9 times bigger than the other, that's not going to have as good of a capacity as if they're equal to each other. Sometimes we have a buffer that we know is mostly going to get acid added to it. We know from what's going to happen, we're not going to be throwing any base at it, it's going to be acid. Well, then we want to put extra base in the buffer so that it has more capacity for the acid. If you need to neutralize primarily base, you'll add more acid. These are just pictures of concentrated buffer, dilute buffer. Any questions? Okay, we have a 1 liter buffer solution. It's 0.1 molar HF, 0.05 molar NaF. Which action destroys the buffer? What's going to happen if we add 0.05 moles of HCl? HCl is a strong acid, right? And so we don't care about the chloride. We're thinking, oh, we're adding acid, right? What's going to happen? Is that going to react with this or with that? It's going to react with the NaF. There's 0.05 moles per liter. We have 1 liter of this. So we have 0.05 moles of this. Can it react with 0.05 moles of acid? It can. But then is there anything left for more acid? No. So we can say that destroys the buffer. So this destroys the buffer. What if we add the same amount of sodium hydroxide? Again, we're not interested in the sodium, we're interested in the hydroxide. The hydroxide reacts with the HF. 0.05 moles, 1 liter of 0.1 molar. This has 0.1 moles. If we neutralize this, we still have 0.05 moles of it. So now the buffer's actually a better buffer because we'll have equal amounts, right? That's not going to destroy the buffer. What if we add 0.05 moles of NaF? That's this guy. Well, we were kind of short on that one to start with. If we add more, now they'll be equal. Better. It's not going to destroy it. Any questions? Yes. Yes, it'll be more effective if it has equal concentrations.
Okay.
And the reason that you wouldn't always have equal concentrations is if you want a buffer that's not at the pH, which equals the pKa of your buffer system.
Okay.
So then you have to make one higher or lower to adjust the pH.
Are you doing lab
We're doing a lab that has calculations about buffers in it.
Okay.
Yeah. Mhm.
Would you mind basing why A is the correct answer?
Pardon me?
Would you mind explaining why A is the correct answer?
Okay, so A is the correct answer because adding hydrogen ion, there's two parts of this buffer, right? This is the acid and this is the conjugate base. Again, let's just cross him out. The sodium's not doing anything, right? So there's this F minus. When we add H plus, it's not going to react with an acid. It's going to react with the conjugate base. It's going to make more acid. And because this is 0.05 moles, and this is 1 liter of 0.05 molar, it's also 0.05 moles. So it's going to use up all the F minus. It's going to turn that into HF, and then we're just going to have a solution of hydrofluoric acid. It won't be a buffer anymore.
Then what B and C allow for?
B and C do not destroy the buffer. In fact, they actually make it better. Because here, by getting rid of some of the acid, we end up with equal concentrations of acid and base. This is an okay buffer. This is a fine buffer. There's nothing wrong with it. But if those are equal, it is actually a little better. And here, if we're adding more of the base, which again is low, again, we're going to get to equal concentrations, which is better, definitely not destroying. Any other questions?